Hey everybody, welcome to the second part of this tutorial on how to transform an image into a particle system. So this is the patch as we left it on last tutorial, the part 1. There is a couple of things I want to say before we start. First of all, I attached a message box with enable written and $1 so we can enable or disable the transform feedback. This will kind of start the process of feedback for the buffer objects that are here. So if this is not enabled, basically the process doesn't start. Then, as Pedro Santos wrote on a comment on my previous video, instead of using root dim and prepend dim, we can actually just use the root pass object, which is very cool. So we just say root pass dim. And this should basically work as it should just pass the message dim out of that. So let's try. Yeah, it works. Cool. So thank you, Pedro, for this tip. It's really cool. I didn't know about this object, I think. Okay, so let's get to business and let's go inside our code here, because basically we did everything, almost everything we could do here. We now need to delve into the shader code. Or maybe let's also color those objects with a color, just to make a bit more clear that these are kind of special objects. Okay, and then maybe also the shader object. It's kind of more clear if it has a different color. We can always identify it immediately inside the patch. Okay, so we open our shader code inside an external editor, which is Visual Studio. If we want, we can also change the shader name. So, for example, image to particles shader. Description, default shader, let's just delete it. And let's go on. So what we want to reach in this algorithm is to be able to move the particles that compose this image, move them away from our mouse. So what we need to do, first of all, is to get the position of the mouse inside our shader. So we will create another parameter to do that. So let's do it, paraname equal, can call it uMouse pos. I call it uMousePos because U stands for uniform, because this is a uniform variable. It means that is uniform through basically all the different kernels that execute the shader, but it's just enough to think about it like it's something like an external parameter that we can input inside our shader. It's different from the buffers that we input here, because these are state parameters, let's say, and this is actually is a uniform parameter that is the same for all the kernels. So type, this will be also a vec3, and then not state but default, so we give it a default value of 0.0, 0.0, 0.0. We create a three-dimensional vector, even though if we are going only to use the x and y position of this vector, components of this vector, we are not going to use the zeta, but since we are working in kind of a three-dimensional environment, let's give it also a z value of 0. And then we have to bin this parameter here. So bin param uMousePos program. It will be the vertex program. Okay, cool. Then what we want to do with this, with the mouse position, is to get a vector that goes from each particle to the mouse position. Or actually we want to do the other way around. So we can do that like this. Let's call it from mouse direction, or maybe direction from mouse. So this will be our position, so our input position, minus the mouse. So mouse pos. Oh, and of course I forgot to add the mouse as a uniform as a variable here. So let's do it. Let's write uniform vec3 mouse pos. Okay, so now it exists inside our program. Okay, so this is the direction of every particle to the mouse. So it's a vector that points from every particle to the mouse, simply by doing this little subtraction. Let's now normalize this direction. So let's say norm dir from mouse. Let's use the normalize function to normalize dir from mouse. So the direction of the particles from the mouse. And then let's also get the length of this vector. So how far basically are those particles to the mouse? And will be a float. So because length is this is a scalar, the length. So we can call it dist from mouse, and this will be the length of dir from mouse. So not the normalized one, because the normalized one will always have a length of 1. Actually of the original vector. Okay. Now we want to use the normalized direction vector to basically create an acceleration vector that will be added to our velocity in order then to move our particles. So let's do like this, vec3 acceleration. So this will be the acceleration of our particle in this frame. On this frame and then for all the other frames. So acceleration norm dir from mouse, and then we have to we use the normalized the vector because then we are sure about what is its magnitude, and the magnitude will always be 1 because it's normalized. So then we can multiply this for a value, and this will give us how much each particle will move in each frame. So for this specific force, so let's maybe multiply this by 0.0 something. On my code I say 0.0 cents, so this is what I will write also here. Okay. Then we want to divide the acceleration by the distance squared from the mouse, which means the particles that are farther from the mouse will not be affected from this force, and the particles that are closer will be affected the most. Okay. So let's first get the value of the distance from the mouse squared. So let's do like this. Dist from mouse squared, and this will be equal to dist and multiplied by 2, because we are dealing with very small numbers here, right? We are dealing with very small numbers because the maximum distance is minus ratio, and on the epsilon is minus 1 to 1. So these are very small values. So if we get so if we take at least the double of the distance, we start to get somewhere. And after we do this, this will be not enough. So let's actually multiply this by 2000 just to be sure, because we are dealing with very small small numbers. So even when the mouse is far from the particles, this will actually not affect very much the force unless we multiply this distance for a big value, and then in this case the force is going to be reduced, because then we're going to do like this. So acceleration divided equal to the distance from mouse squared. And let's add a small constant just to avoid that the force will be divided by 0. Okay, because this will yield an unexpected result. So let's add this small constant. So like this. Okay. Okay, after this we are basically set. Then we can say the velocity. So velocity it's equal to the acceleration plus the input velocity. Okay, so we basically loop back the previous velocity, added a new acceleration that will be probably different, could be different from the one from the previous frame, and then we output the new velocity as this. Okay, so after this, let's actually clamp the output velocity before we output it. Let's clamp this between two values, because so it will not get too peak. So the particles will not start to fly around at infinite velocity. Okay, so let's do like this. Clamp output velocity, so the one we have to output between two different values. So between vector 3 minus 0. So on my code I wrote 0.04 and then another vector 3, 0.04. You see that we're using constants, but actually would be much better to transform these values into variables, and even much more better to transform those into parameters that we can then modify from outside the GLSL code. So let's actually start to do that. So let's create a new parameter, param name U as uniform, max velocity, so max vel, type, this will be a float. Default, let's give it the value that I just used, so 0.04. Let's close that. And let's of course bind it to the vertex program. So U max vel. Okay. So let's take it. Let's declare it here. Uniform float un max vel. And let's actually substitute, replace basically those numbers with this value. So minus U max vel, U max vel. Cool, so now we clamped the velocity. So now we can actually start output our position like the sum of the previous position plus our new velocity. So plus output velocity. Our color will just be the same as it was, so it will stay the color of the pixels, and the original position will remain as it is. So for the moment we didn't use the original position, we will use it in a second. So everything looks good. We could even try to see if it actually works, but before we need to actually get the position of the mouse. So in order to get the position of the mouse from the window, we have to send to the window object inside the JIT world the message idle mouse 1. And this we can attach to a load bank, so this will be done automatically when the patch gets loaded. Ecco qua. And then we actually need also the size of the window, so we can use a get at object to get the size of the window. So this, every time we modify the size of the window, this will give us the size of the window. Then from here, let's route the mouse idle message, which will give us the coordinates of the mouse, exactly as you can see. But these coordinates are in pixels, and we have to transform them in values that go between minor ratio and ratio for the x, and 1 and minus 1 for the y. So how do we do that? It's very easy. First of all, let's unpack just the first two values, which are the one we are interested into. So let's use a message box for that. And then let's use a Bexp object to say that we want to divide the input divided by the second input, which is the list of the dimensions. So we will get values in between 0 and 1. So let's modify the window to send the list inside the Bexp object, and we are good. We are outputting values between 0 and 1 on both dimensions. Cool. Then what we need to do is to scale them between minus 1 and 1. So let's create another Bexp, and let's say $f1 multiplied by 2, and then subtract 1 to that. Let's also say it's color mode 1, and we should be good. We should have values that go between minus 1 and 1. So we multiply by 2, and then we scale, and then we subtract 1 to that, so we go between minus 1 and 1. Okay, looks good. Now we need to multiply the x value by the ratio. So let's unpack, and let's multiply only the x value by the ratio, which will be actually these numbers, one divided by the other, so like that. So how did we call this parameter? we called it u mouse pos. So let's say pack u, actually param u mouse pos, and then f and 0. So this goes here, the y goes here, and we are good to go, I think. Let's connect this to the shader object, which is down here. So maybe let's make a send u mouse pos. Let's receive it here at the shader. So this will be the position of the mouse in normalized coordinates. So let's maybe try to activate our transport feedback, and I see that I get an error. Oh yeah, and of course the error is that I use dist here, but it's actually, it's not called dist, it's called dist from mouse. So sorry for that. Actually called dist from mouse. So maybe now it could work. Yeah, it's starting to work. Let's go full screen. Oh, and of course, if we go full screen, we don't have any way to enable the transfer feedback. That's why we can use the key object. Let's say cell32, which is a space bar, and then we basically, let's say, every time we press the key bar, the space bar just enable the transfer feedback. So let's go full screen. Let's press the space bar, and you see it's actually working. Now the only thing that is not working is that the y mouse position is inverted. So that's typical because the y mouse position goes somehow in the opposite direction when we convert it into the OpenGL world. So what we need to do is to simply multiply that by -1. So the y position, we have to multiply this by -1, right? So let's try again. And let's hit the space bar, and now it's working. This looks good. Now this looks good. The only thing that bothers me a bit is that the particles move all with the same speed, which is not super nice to see. Oh, let's actually say not select one, not say one, but simply just send a bang to the toggle. So we can start the transfer feedback and also stop to reset kind of to the image. Okay, so in order to solve this thing that the particles get all move all with the same velocity. Oh, and also let's attach this here because then we can see the actual values of the pixels. Right. So to solve this problem that the particles move all with the same velocity, we can multiply the acceleration for example, the value of the colors. So we can use the value of the colors of the pixel to kind of create a random difference. Not really random, it's related to the colors, but we can create a difference according to the actual color of the pixel. So we can do something like this: iColor.red plus iColor.green plus iColor.blue. I don't know why they are blue, these variables. It's kind of interesting. We can sum these all together, multiply it by 2, just to make it a bit more interesting, and then add 1 to that in order to... also, if we have black, it's not going to multiply the acceleration by 0, right? Okay, so let's try again. Let's go full screen. Let's try... And now the particles move a bit more randomly, which makes it much more nice. So our tutorial could theoretically stop even here, but we got some more stuff to do, haven't we? So let's do a couple of things. First of all, we may want to modify the force of this acceleration using a parameter. So from our patch, so let's actually copy the parameter. Let's say mouse force or something like that. Default will be 0.007, and then let's bind it. So mouse force. Cool. So now that we bound it, we can declare it here. So uniform float u mouse force, and then we can use it instead of using this constant here. Right. And okay, for the moment this is good. Let's now create the force that will attract our particles back to their original position. Okay, so that they can actually go be displaced, and then they can go back to their original position. We can also make this this force optional, so we could say, okay, don't apply this force, for example, by multiply the strength of this force by 0. Otherwise will be applied. So okay, let's start with it. So let's go here and let's create this other force. So force from position to original position. So the initial position where the particles were. So we have to do like this. So vec3 dir from dir to origin, let's say. So this will be our position. No, sorry, the input original position minus the position we are currently in. Okay. Oh, and it's actually called I-pos origin, right? Then we have to normalize this force. So norm dir to origin equal to normalize dir to origin. And then we get the length of these vectors. So dist from origin, let's call it. This is the length of dir to origin. Okay. So now after we do this, let's add to the acceleration. Let's add this new force. So norm dir to origin multiplied by some number to reduce this force, let's say 0.0009. Then let's multiply also that by the distance. So in a way that when the particles are close to their original position, they will actually stop to move, because then will be multiplied by 0. So let's multiply that by dist from origin. And let's maybe multiply this value by half this value, just to, these are just numbers that I got experimentally, otherwise the force will be too strong. So this should be it. Let's take a look and see how this looks like. So, oh, right. I forgot, for some reason, when we do this, the image will just start to bounce, because for some reason it's not attracted. It's not attracted directly to the original position. For some reason, it's attracted to some force that brings it up and right. Okay, so this is a bit annoying. So what we can do, is to basically create another parameter here. Let's call it u drag amount. Type will be float, and let's say default will be equal to 0.0, no, sorry, default will be 0.99. Let's bin this parameter. Oops. Let's declare it. Uniform float u drag amount. And then what we want to do is to basically, after we use the velocity to update the position, let's maybe multiply the velocity, the output velocity. Let's multiply it for drag amount, so u drag amount. Alright, so if we go here, let's actually create those parameters that we declared. So we got u max bel, so param u max bel $1. Modify this with a float number. Then we have got u mouse force. Then we have got u drag amount. Oops, mistake here. this must be attached. This must not be here. So you drag amount. Right. So okay, now it kind of fixed down. So let's see if this works. Okay, so as you can see, the particles after they have been misplaced, they will just go back to their original position and then stop there, because they're multiplied. The force is multiplied by the distance. So when the distance is very few, they will stop moving. So when we start, there will be this awkward thing that basically the image just starts on the right and going up, right? And then we can actually, it doesn't even interact with our mouse. And then when it actually stops, we can, in theory, interact with it. For some reason, it's not working. So let's check why. First of all, let's actually send some load mass to those number boxes. So max value, we say 0.04. Mouse force, we say 0.0007. And drag amount is going to be 0.99. So let's fill those values. And let's try again. Okay, so now it's working properly. So let's see, we can do one thing. When we go full screen, we can say basically the drag amount goes to 0, so we will avoid this awkward thing that the image flies on the top right. If somebody knows the reason because of for that, please comment this video or tell me in some other way, because I'm really curious. So I could not figure it out why this image has to go up on the right. Let's maybe change image. Let's go with the MOT. And she also goes up and right. So I wanted to say that we can kind of fix this by doing something like this. So select 1 0, and we can do like this. So when this is enabled, we want to go to 0 with the drag amount, and then maybe delete 1 second. Then go back to our original value, which would be in this case 0.99. So let's try. Okay, so we stopped, and then so we avoid this awkward thing that the image just flies up on the right side. Okay, so let's see. Right, so this looks good. This looks good. So this looks good. The image slowly recompose itself. Okay. So this looks actually pretty correct. Of course, we can modify the various forces. Let's actually also add the force to a parameter to decide the force for which the image recomposes itself. So we can also set it to 0 if we want to completely avoid that. So let's create another parameter. Origin force amount, something like that. So default we say is 0.00009, so 0.00009. Okay, let's bind it. All right, and then let's declare it. So uniform float this. And let's use it instead of this constant here. Right. So let's create, let's copy one of those. Let's put it here. Right. So if we want to set this to 0, and let's set the load mass to 0.009 or something like that. So if you set this to 0, then the image basically will not recompose itself. Let's set this to 0. No, okay, it doesn't seem it's doing what I wanted it to do for some reason. It's just kind of, it's not really doing what I wanted it to do. It's doing something strange. Okay, let's check out exactly what is not working. So if we do this, the image recomposes itself. Right. Then if we set this to 0, I would expect the image doesn't recompose itself anymore. Ah, okay. And it's exactly what is happening actually. Okay, so everything seems to be working correctly. Let's just close the patch and reopen it just to check that everything works again out of the box. So, select an image. Let's take again the mouse. Start, right, let's go full screen. It goes back to its original place, and this is working. Okay, cool. Then it recomposes itself. Right. Then if we set this to 0, go full screen, activate the transform feedback, and okay, for some reason, when we go full screen and we activate the transform feedback and we set this to 0, then it kind of the mouse force is much lower somehow for some reason. But if we bang again here and give it a bigger value, okay, so let me debug 1 second why this is happening. Okay, I think the problem is just it's just here. So let's simply say if u origin force amount is greater than 0.0, then do that. Otherwise, not. So if we set this to 0.0, let's take a look. Right. And it's now working. Okay, if we set this to 0.0, right, and now it's recomposing itself. Okay, so, oh, finally it's working. Okay, cool. So yeah, we created the image to particles using the GL3 package. So that was it for this tutorial. You can download let me put myself in the center. You can download the final patch on my Patreon, if you are a patron of mine. Otherwise, you will have to do it the hard way and just follow the tutorial along. And if there are some questions or problems, just write me. I will make sure to answer every problem that will probably arise. General questions, I am also here. So thank you very much for following. Hope this was kind of useful to you or enjoyable. So see you in the next tutorial that will come probably soon enough. Ciao.